Well, you can divide chemical warfare agents into four main categories. The blood agents, these are compounds that react with hemoglobin and basically suffocate you. You can't get oxygen. Choking agents, phosgene and chlorine are the two examples that we'll talk about mainly. Blister agents, mustard gas is the prototype. Lewisite is another compound we'll talk a little bit about. And then, of course, the nerve agents that have been in the news a lot the past 2 weeks. But in fact, chemical warfare goes long before World War I in 1915, as you can see. Natural products are very poisonous. Botox, that most toxic single molecule known to man, is a natural product. And some of these compounds were used by these indigenous Indians and tribes in the Amazon in South America to poison their arrow tips, and this was a form of chemical warfare. Here's another compound we did talk about, very, very toxic compound. Actually, you can see it on the back of this frog. That shiny appearance is due to epibetadine, this extremely poisonous compound. But going way back, as you can see, people recognize the fact if you burn sulfur, and in fact arsenic was around, these were used in chemical warfare. Another example, again, if you burn sulfur, you produce SO2. You breathe SO2, it becomes sulfuric acid in your lungs and in your nose. This was used, as you can see here. Da Vinci actually proposed using, again, arsenic, sulfur, or a sulfide in chemical warfare. And here's another example of this very poisonous alkaloid, atropine, used in this siege back in 1672. Ironically, as we're going to see near the end, atropine is one of the two antidotes for nerve gas poisoning. Chlorine was actually first proposed in 1862 during the American Civil War by a New York school teacher. He proposed to Lincoln, and I've seen a copy of a letter where he wrote to Abraham Lincoln proposing that we use chlorine gas against the Confederates in the Civil War. And they rejected it. I'm not sure why, because it actually would have worked, of course. But then it was not used, as you'll see, for another 50 years. Various treaties were proposed and adopted, but never really followed, as it turns out. Again, some of these you don't have in the syllabus. Well, chemical warfare involving true, pure chemicals really started with the French, and they started using ethyl bromoacetate against the Germans. Now, this compound never killed anybody, but it's a good tear gas. Anytime you have a bromine or a good leaving group on a carbon attached to any carbonyl, that will be a potent tear gas. And this is one of the ones. And in fact, the ocean, sponges and seaweeds make things like this, as we've talked about a couple of times. Then the Germans actually used this particular biphenyl, and I'm not sure why this is so toxic. Again, I think it's just a tear agent against the British in 1914. The Germans then also used a tear gas, and again, anytime you have a benzylic halide, a leaving group on the benzylic carbon, that again is a potent tear gas, and this was used in this battle against the Russians, the Germans against the Russians in Poland. It wasn't very effective because it turns out the front was so cold the compound didn't evaporate, it just kind of laid there in the trenches. But then the Germans got serious in 1915. And this was April. This part of Flanders in Belgium, Ypres, and you can see near Antwerp and Ghent, where a lot of the World War I battles took place, as you may know. They used chlorine gas. They opened the cylinders, and the French and the Canadians as well, 2 days later, totally unprepared. They had no idea what was coming. Wind conditions were right. Chlorine is heavier than air, about twice as heavy as air. It rolls across the battlefield and causes death. And again, they used it 2 days later against the Canadians. It was so successful the first time on April 22nd. But in fact, chlorine, as you may have learned in general chemistry, is very easy to reduce. You can break the chlorine-chlorine bond with sodium thiosulfate, reduces it. So that was put into gas masks, and that detoxified the chlorine fairly rapidly. But then the Germans put chlorine into artillery shells to get it into the trenches before you had a chance to put on your gas mask. And you can see that was used a few months later after Ypres. The British finally said enough is enough. They started using chlorine against the Germans later in, again, 1915. Then the Germans used phosgene. Phosgene we've talked about in this class already. It's a way to make carbamate pesticides. It's a double acid chloride, very reactive, much more toxic than chlorine. And in fact, it has an odor that is really pleasant. When you mow the lawn, that smell, in fact, you'll smell that in the spring when the college begins to mow the lawns, is exactly the same smell as phosgene. Not the same compound, obviously, but has the same odor as phosgene. It's very insidious. So you smell it, smells nice, and gets in your lungs, and basically you drown from the inside out. What these compounds do, they dissolve the tissue, separating your plasma from your lungs. Fluid seeps into your lungs. That's what happens with chlorine and phosgene. Then the Germans actually put vomit gases in with the phosgene. And so even though a gas mask, charcoal gas mask, would protect against phosgene, the vomit agents would penetrate the gas mask. You'd have to take off your gas mask and then be exposed to the phosgene. And these compounds were later developed actually at Illinois in the chemistry department. So the British then started using phosgene as well against the Germans. And then 2 years later, the major breakthrough, the discovery, the invention of mustard gas, again by the Germans. They were the best organic chemists in the world, even though mustard gas, really a liquid, was discovered about 50 years before this. The reason it's so effective, it doesn't have to kill you to cause a casualty. The blisters are so painful and so infecting as well that you just can't fight, even though you're not going to die necessarily. And then the Americans started using gas for the first time, probably phosgene, we think, initially, and then mustard gas as well. So this kind of summarizes the major developments in World War I, and the 3 or 4 gases that were used then. And you can see most of the fatalities came from phosgene, actually. But most of the casualties actually came from mustard gas. But again, most of those who were gassed with mustard survived. They just couldn't fight. Again, Pershing had this to say probably around 1918 or so. And of course, we know that this is going on right now in the Middle East. Okay, just to summarize, this now is in the syllabus, I think. You can see a summary of developments here. If you have any questions, just kind of yell out. It's hard to see your hands unless I'm looking. And again, the results. Okay, Haber started things in 1915, the Western Front, World War I. His wife was also a chemist, and she was so upset after these 2 gas attacks that killed probably 1,000 soldiers, maybe more. She committed suicide 2 weeks after the gas attack as a protest. And their son did later, in fact, also committed suicide. Here's some photographs showing the gas attacks. Again, these cylinders, it's probably chlorine, I would guess, but no way to know for sure. And again, the wind conditions have to be just right, because if not, of course, the gassers become the gasees. And that happened on occasion. Gas alarms. just a giant bell you'd ring. A gas cloud is coming. So put your gas mask on. Again, mustard gas effects. You can see that just horrific blisters here. These awful things. You just could not fight. You could not hold a rifle. But you would live. I went to Ypres in Belgium about 10 years ago. And the trenches are still there, actually. Although the trees have grown up around them, of course. I almost tried to take a few of these home in my suitcase. I decided, no, maybe that's not a good idea. And cemeteries everywhere in this part of Belgium and France. This is John McCrae's famous seminar poem that he wrote on the battlefield. He died later, actually was killed there. But you may have read this in high school in Flanders Fields. Okay, in World War I, literally chemists on both sides, especially in Germany initially, were taking chemicals off the shelf, just testing them against animals, and in some cases against people to see how toxic they were. So again, we have the tear gases. This is mace. We made this in class on the blackboard. Methylphenyl ketone, chlorine, and acetic acid. So acid catalyzed alpha halogenation of a ketone. Well-known reaction. And again, here's the haloacetones. Some of these are produced in the ocean and other compounds. All of these are potent tear gases. The choking gases, again, it's kind of a euphemism, they choke you to death, are chlorine and again phosgene. But other compounds have been used. Some of these have been used by Russia against some of their former countries in the Soviet Union. The blood poisons, hydrogen cyanide reacts with hemoglobin. Very toxic compound, of course. And cyanogen bromide and chloride also have the same effect. Blister agents, again, refer really to mustard gas, and lewisite was invented in this country and was almost used in World War I, but in fact, the armistice in 1918, the end of the war, stopped the use of lewisite. It was on a ship actually going over to France at the time. And then the vomit gases I mentioned. Here's lewisite, very simple compound like mustard gas. You just take the arsenic trichloride and acetylene and you get this compound. It's like mustard gas. It causes terrible blisters. First synthesized in this country, as you can see, and named after this guy. So here's a laboratory at Catholic University in DC where it was first made, and then later at Notre Dame, actually. You can see the blisters, just horrendous blisters. And they get infected. They pop, obviously, leach, and then get infected. This guy used to live in Hanover, and he is really the father of chemical warfare for this country, James Conant. And in fact, I met him once. He used to do research, library work in this building when the library was up where, I forget where it was. I think on the second floor. 201 used to be the chemistry library in Steele Hall. And he lived here for a while. And in fact, died in Hanover. Okay, after World War I, we have some incidents of where the Soviet Union used gas, probably mustard gas and phosgene. 1921, you can see it was used in Morocco and also in Ethiopia, where Mussolini actually used mustard gas against the Ethiopians, and they fought in bare feet, and so they were running through the battlefield through pools of mustard liquid. It's actually talked about in this book if you ever read any of his novels. The Japanese, we know, used gas against the Chinese in their long-standing war, 1937 to 43. And hydrogen cyanide was actually found in World War II in some of the Pacific battles, Guadalcanal. This is a famous case, actually, and this was investigated, discovered by a guy, again, Dartmouth class of 34, who took chemistry in this room, again, of course, and got an MD here as well. And I'll come back to that. But basically what this was, a cargo ship in 1943 in a harbor in Italy was carrying mustard gas. This was top secret, and we were prepared to use gas for the first time in World War II if Germany did, which they never did, of course. But the ship was sunk, and the mustard liquid spread over the harbor and actually killed about 83 sailors, mainly. And nobody knew what it was. It was this oily liquid that caused all kinds of burns, and Dr. Alexander then went over there and actually identified mustard liquid in the harbor. And just some other facts as well. Here's where the John Harvey was. And again, it was sunk by the Nazis. And then the numbers here refer to the number of fatalities, in fact, on each ship. And again, Alexander identified the liquid that was in the harbor as mustard liquid. And again, here he is. And he lived, where did he live? Not sure where it's at. Oh, top left. Okay, then we come to the 1980s, 1990s, the long war between Iraq and Iran. Saddam Hussein clearly used nerve agents as well as mustard gas and phosgene against the Kurds for sure. And your parents might recall these terrible Scud rocket attacks from Iraq into Israel, and we were afraid that those rockets were going to be loaded with nerve agents, which Saddam Hussein had at the time. Fortunately, they weren't, but this was a terrible time for about a year. And of course, more recently, as you know, Syria has used Sarin. And even this week, it was reported using chlorine and mustard against civilians. Mustard gas, very easy to make. You take ethylene, sulfur dichloride, and this was synthesized way back in 1822. This is, again, it's called mustard gas, but it's actually a liquid. It has a high vapor pressure, dispersed as an aerosol, but it's actually a liquid. And here is the first tear gas mace that we've talked about. Here's pepper spray. It's on the last exam without the chlorine, and one of the vomit agents. And you can read about pepper spray. Again, it was synthesized at Middlebury College, and this journal is up in Kresge. Yeah, Julianne?
Vomit agents make you vomit?
Make you vomit in your gas mask, and you have to take it off, or you'll choke to death. And then you're exposed to phosgene or another gas. Okay, the nitrogen mustards were unknown compounds until the end of World War II, when they were uncovered in Germany. And the thinking was because they're stable in water, but they undergo reaction like the sulfur undergoes cyclization to give a three-membered ring, can cross-link DNA and proteins. The idea, we think, that the Nazis were going to use this as a water contaminant. They were going to sneak a saboteur into, for example, London and dump this in the water supply of the population. But that did not happen, in fact. Now, in fact, these are used as anti-cancer drugs because they do react selectively with cancer cell DNA. Now, the US and this country, even though we didn't have nerve agents, as you'll see, they were testing lots of other things. They were trying to make things more toxic than phosgene. And here are some of the compounds they tested. You can see instead of chlorine, they have fluorine on the carbonyl and other compounds they were testing, including a test on Mount Shasta up in Northern California, this beautiful 14,000-foot mountain, until they discovered, when they tested a sulfur compound that's non-toxic, it drifted, rolled down the mountain into the town of Shasta City. So they decided, well, we better not test phosgene on Mount Shasta. And again, another case that involves actually a professor here at Dartmouth, used to be here. His son was actually, well, his father was killed using phosgene. Again, here's Mount Shasta, this beautiful mountain up near the Oregon border. They were going to release phosgene someplace in here, and the city's right down here. So that never happened. Okay, then things really remained about the same until the nerve agents were discovered. But actually, this goes way back to Clermont in France, the French chemist, tetraethylpyrophosphate, the first organophosphate to be toxic. But they never realized it because he was not a very good chemist, very nice guy, but not a great chemist. All these guys tasted the preparation, and by rights they should have been killed, but in fact, nobody even got hurt. But we know now today that in fact this compound, the first organophosphate, very toxic, LD50, extremely low, of course, as you can see. But then in Germany, Lange and Kruger knew about the early work of tetraethylpyrophosphate. They started investigating these compounds as potential new insecticides. Germany could not import nicotine during the war. Nicotine was the only good insecticide. So they had to make their own, and they were trying to make these compounds. These compounds, they noticed, difficult in breathing, choking sensation, difficult to see. And this is characteristic, as you'll see, of organophosphates. But fortunately, because the R groups are fairly small, your body can reactivate the enzyme, as you'll see. But they noticed this, and again, this journal's up in Kresge. And this is what you always experience when you've been exposed to an organophosphate insecticide or a nerve agent. But in fact, Germany at that time, again, this is 1932, they were not interested. They didn't see a future in this, at least initially. But then later on, they did, as you'll see. But Lange was married to a Jew, and so he was forced to leave Germany, went to Canada, and then eventually retired or worked in Cincinnati as a chemist. But then Gerhard Schrader took up the Lange work, fantastic chemist, and he was the first to synthesize Tabun, the first nerve agent, and Sarin in 1938. In contrast, Saunders in England, with a very large group, were trying to make new warfare agents. They made no bones about it. They were trying to make things better than mustard, better than phosgene. Whereas the German guy, Schrader, was really just trying to make new insecticides. The best thing that Saunders came up with was DFP in 1941. Later, when the war was over, they made Tabun. Soman, in fact, was made actually by a guy, Richard Kuhn, in Heidelberg. Soman is the most deadly of all the initial nerve agents because it's a very bulky alkyl group, as you can see. And again, he was a true Nazi. He insisted on the Nazi salute before his lectures. Yeah, he denied working on this after the war. Now here's the Nazi salute, as you may know. Now this guy is not saluting, which is a major mistake in 1936 in Nazi Germany. If you're not giving the Hitler salute, if you will, you can see he's not doing it. And the camera caught him. I'm not sure what happened to that guy. And Richard Kuhn later on. Okay, so by the end of World War II, the Germans had actually built a plant in what's now Poland for synthesizing 1,000 tons of Tabun per month. They had stockpiled 12,000 tons of this agent ready to be used in warfare. It never was. We'll talk about that in a minute. Sarin, well, this plant was actually captured by the Russians, and they identified the compound eventually. They dismantled the plant, literally bolt by bolt, took it back to Russia, reassembled the plant on the Volga River, and Tabun then became the standard Russian nerve agent in 1945-ish. The Americans were not quite so lucky. We were advancing, of course, from the West, and we stumbled on a plant making sarin that was under construction, but we did capture a small amount, and we identified that. And sarin became the standard nerve agent in this country for a long time until the the mid-50s or so. And again, the Allies had no idea what was going on. This was a huge surprise that these compounds were known, in fact, and the fact that Germany had synthesized so much of this. The U.S. came close. In 1942, in this country, we did test these compounds, but for whatever reason, they decided, well, they're not toxic enough, they're unstable, and was never pursued. The organophosphates were never pursued. Okay, going back to 1936, again, he was a chemist working in Germany, noticed when he made Tabun, same side effects, difficult to see. You get meiosis, the pupils contract, very difficult to see, hard to breathe. And they had to stop work for a long time. But they decided, in fact, this compound's way too toxic to be used as an insecticide because the sprayers would die, probably. But what they had to do in this war, Hitler demanded that any potential use to the warfare agent, not agent, but effort, sorry, had to be reported to Berlin. And so he did report this discovery to Berlin, and then he was forced to change jobs, basically, and then start making warfare agents. No more insecticide, you make better nerve agents. And here he is later in life. Here's his laboratory. He was an amazing chemist. He made hundreds and hundreds of extremely toxic compounds and survived. It's just an amazing story. Again, Tabun and Sarin, the first two to be made. They were given these secret codes. Trilon 83. Trilon actually referred to a detergent used in Germany during the war, and so they wanted to cover up the name of these things, so they were actually named Trilons. In 1970, I actually wrote a letter to him, or 73, yeah, 73. I wanted to find out more, so I was kind of a naive, brash assistant professor. Is it really true that you invented nerve gas? And he wrote back and said, yes, I did. Here are the references. It was amazing. Here's his autograph and the references. So again, he discovered first Tabun, and then he was moved to a different factory so he could make better agents without being disturbed, no more insecticides. And then Sarin in 1938. Now, Sarin is much more toxic than Tabun, and even though it's a liquid, it has a high vapor pressure, so it really does act as a gas, even though all of these things are liquids. And it's named after him, Ambrose, one of Hitler's best friends, Van der Linde, who actually discovered Linde, we talked about earlier. They started testing Sarin in 1939, probably on prisoners. In 1939, of course, in September, Germany invaded Poland. That's what started World War II, as you probably know. And Hitler went on the radio and actually announced that Germany had these new weapons and the enemies will be defenseless. And I think he may have been talking about the nerve agents, because at that time, Tabun was well underway. The plant was almost ready, and they had a lot of samples of Tabun at least. Many, many accidents, of course, because they were really pressed. They were in a great hurry to make these compounds. You know, they were starting to lose the war, of course. Well, maybe not in 1942. Again, here's Poland, and the plant was around here someplace. Lots of problems, you can imagine. First of all, the antidotes were not developed until much later, as you'll see. Albert Speer, actually, in his autobiography, I have a copy of this book in my office, he got a sample of Tabun. He was intending to kill Hitler. And just before he was going to do it, again, according to him, self-serving perhaps, Hitler had the ventilation shafts of his bunker raised way above the ground. He was worried the Russians might try to poison him with a knockout gas, but ironically it prevented Albert Speer from dumping Tabun into the ventilation shaft. Now Hitler was gassed in World War I with mustard gas. He knew the effects of war, of gas warfare, and early on in the war, or about halfway through, he wanted to use nerve agents, the new one, Tabun, against the Russians in particular. But Ambrose convinced him that the Allies clearly had the same compounds. Retaliation would really be severe. So Hitler then decided not to use gas against the Russians until later in the war. Early in 1945, apparently, he did give the order to use Tabun and Sarin, maybe, against the Russians, advancing, of course, into Berlin. The generals refused to carry out the order. They knew the war was lost. Why make it worse? And so they never carried out the order. So gas, at least nerve agents, were never used in World War II, at least in Germany. So this just reiterates what I just said, I think. Again, the Allies had no such capability. Even though if they really looked around in the literature, they would have found the information. So DFP was the only thing they did have. Again, this is, ironically, this is used to treat eye diseases. It's fairly non-toxic as these things go, developed in England. And they did test it on themselves. Sanders actually tested it on himself. And again, you see meiosis, this contraction of the pupil. And even after the war was over, then everybody knew what sarin was, and so all the countries began to test it, maybe to make it their own nerve agent. And this might have been the first guy that actually died. He wasn't very big. He was only given about 20 drops. That's a pretty small amount on his skin, actually. So it penetrates the skin, and he died. And this was, again, top secret in the UK for a long time. You can see this euphemism here. And you can see much, much later, it was, they admitted, okay, we made a mistake. But again, he was unlucky. He didn't weigh very much, and he lacked this enzyme that will reactivate the damaged enzyme, as you'll see. Okay, then about 10 years later, in the mid-50s, again, some guy in England, an Indian chemist working in England, trying to make new insecticides, discovered VX. And the V stands for velocity of action, I think. But he was making these compounds, and these are just like the other organophosphates. The only difference, really, is that you have a nitrogen here, and that's, as you'll see, that's key to make it extremely toxic. A lot of countries now have synthesized this, as you can see. This killed a lot of sheep in Utah. There was an accident I'll talk about in a minute that your parents or grandparents might remember this, if they live in Utah especially. It's higher boiling, lower volatility. So this really does act as a liquid on your skin, as an aerosol. Not like sarin, which is a vapor that you have to inhale. VX is a little bit different. In this country, thousands of tons were synthesized in Newport, this should be, I think, Illinois, up until fairly recently. Extremely toxic, 6 milligrams. And again, this is the compound we think was used against the North Korean NAM a couple of weeks ago. Yeah, this was a major disaster. They were doing an aerial test, and the spray tank on the airplane stayed open too long. So a giant cloud of VX aerosol drifted into the next valley and killed all these sheep. They denied it for a very long time. They finally acknowledged and then paid off the ranchers. But had the wind conditions been different, this gas cloud probably would have drifted into Salt Lake City. This is where the test was done. Actually, right in here someplace. Drifted into this valley, and Salt Lake City's right here. And certainly a lot of people live in here as well. Here's the valley where all the sheep were. And again, the proving ground, which still exists in Utah. VX was in this movie, as you may recall. The Russians have their own version of VX. They didn't know about our VX for a while, apparently, but this is the Russian VX. Has the same molecular weight. The only difference is you have a different alkyl group here and different alkyl groups here, but they have the same molecular weight, the same formula, just as toxic, presumably. More recently, they've developed some other agents that still haven't been declassified that are even apparently more potent than VX. Skip over this. You don't want to look at this. It's top secret. Okay, they've been deployed recently, as you know. Saddam Hussein used nerve agents against the Kurds. Also other gases. Again, mustard gas against the Syrians. And this cult used sarin. You may recall this a long time ago, though. The Tokyo subway, they thought, geez, we can release sarin liquid. It would be dispersed around all of Tokyo by way of the subway, the ventilation shaft. The stuff they made was impure, just like the French a long time ago. It only killed 12 people, not thousands they were hoping to kill. And again in Syria, this goes back a couple of years. Again, because of sarin. There's a new sarin that's a little bit less volatile. Instead of an isopropyl group, here you have this cyclohexyl group. Okay, the synthesis, you don't have to know this, obviously. In fact, you should not know this. But it's so easy to make these things, at least on paper. POCl3 that we've used that to dehydrate alcohols. Dimethylamine, sodium cyanide, and ethanol. That directly gives you Tabun. And Schrader had a one-pot synthesis for making Tabun. Very simple synthesis. Sarin, almost the same way. Sodium fluoride, toothpaste, rubbing alcohol will give you sarin after this initial reaction. Yeah?
Nerve agents work by stopping influx of ions.
We're going to talk about the mechanism in just a bit. Yeah. Basically, that's correct, I think, yeah. And again, VX, you can use up your old World War I supply of phosgene by taking phosgene in this compound and then hit it with a sulfur compound to make this, which is VX. Okay, the symptoms. We've talked about meiosis of the eye. Very difficult to see. Your heart slows down. The cause of death usually is your lungs stop working and you suffocate. But everything else goes into convulsions as well. And you can see, here's a guy that's been exposed, a volunteer, where the left eye was exposed to DFP, and you can see how it contracts. You just can't see, and not enough light will go into your eye. Even after a day, you can see the difference. This eye is not recovered fully, where this eye was not exposed. It's important, as we just saw with Madison, you have to get it off your skin. These things penetrate your skin, and this is what we think happened to the North Korean Nam when he was exposed to VX on the face. If you don't take it off right away, you can see all the guinea pigs will die. If you wait a few minutes, you see 5 minutes, only 30% survive. And you can see after 2 minutes, most of the animals will survive. Okay, what makes these things toxic is the bulky group attached to the oxygen attached to the phosphorus, or the bulky group attached directly to the phosphorus. And you can see that if you look at these reactions with hydroxide, the bulky groups here are very slow to hydrolyze. Isopropyl, much slower in terms of a rate constant with hydroxide than methyl. Also, here you have isopropyl. This is now DFP, very slow to hydrolyze. Whereas if you have the diethyl compound, sterically more accessible to attack the water, to attack the phosphorus, you can see it decomposes in 4 hours. And chlorine, of course, would not make a good nerve agent, because the chloride is a better leaving group than fluoride. It would simply decompose in the atmosphere. And you see this with the toxicity as well. So the bulky groups in red, if you have a secondary alkyl group here, high toxicity, because the nerve agent antidotes that I'm going to show you don't work very well. Smaller alkyl groups here, these are all primary. You can see low toxicity. These compounds are not stable. DFP, though, is stable. Sarin, and we think this is why Saddam Hussein maybe didn't use sarin in the Scud attacks, because his sarin had decomposed in the rockets. If you let sarin stand, it decomposes by disproportionation to give these two non-toxic compounds. Even more serious, though, is the E1 elimination to give propene and this compound. And propene is a gas, the pressure is going to build up. And so, in fact, in this country, we had a situation in 1970 where our sarin rockets encased in concrete were leaking, breaking apart. And here's a guy in Oregon actually testing, looking for these leaks without a gas mask for some reason, but I guess he's okay. And again, you're always testing. Here's a rabbit looking for leaks. And again, I got involved in this in 1970 when these leaking rockets in Utah, they had to get rid of these rockets. They didn't know what to do. The proposal was to load them onto a train and have the train go across country and dump the rockets off the coast of New Jersey. 15,000, well, yeah, New Jersey. It's all right, right? Well, it was not all right. In fact, the public became outraged. But as it turned out, it was the only thing they could do. They didn't know how to process these leaking concrete-encased rockets that sarin was coming out through the concrete. So they actually went ahead with this, and they said, well, you dump them in the ocean, sarin's going to instantly hydrolyze, and no fish will be harmed. Well, I did some calculations, and that's certainly not true. Depending on the temperature and the pH, it would probably take more than a month for the sarin to totally decompose. But it was the best thing to do. And the depth of the ocean off the coast of New Jersey is like 15,000 feet. And it was maybe 10 miles off the coast. So you don't have to worry if you live in New Jersey, or if you did. So what we decided to do, this country and really all around the world, rather than have the actual nerve agent in the rocket, in the bomb, make the reaction occur during firing of the rocket and the bomb. This is the binary agent. And here are the two compounds for VX and the two compounds now for sarin. And we think probably the women, one woman in Malaysia during this assassination had sulfur on her hands, and the other woman probably had this compound mixed together on his face, produced VX. I mean, that's one theory, because this reaction occurs very rapidly. And here's a typical binary agent where you have isopropanol here and the non-toxic phosphorus compound here. You fire the rocket, the membrane breaks, mixes, and you synthesize in flight the sarin. So this country had a lot of arsenals and depots, as you can see, where we had nervic gas and delivery systems. Okay, how does this work? It's a very simple reaction. acetylcholinesterase in all of us, all living things basically, it's in your muscles, in your blood, red blood cells, hydrolyzes acetylcholine. Hydrolysis of an ester, which as you know from the last exam, doesn't go just in water, but this is catalyzed by an enzyme here. Very simple reaction, you break this bond, you form acetic acid and choline. But this happens incredibly fast. These enzymes are so efficient. The turnover number is 20 million molecules per minute for 1 molecule of enzyme. So if you kill 1 molecule of enzyme, you do a lot of damage in terms of nerve firing, as you'll see. Here's the enzyme. I showed you this the other day. Here's the active site. Acetylcholine is right here. So what happens, it gets into the active site of the enzyme. The positive charge on choline is attracted to the negative charge, aspartic acid perhaps, the enzyme. Serine, nature's source of hydroxide, then attacks the carbonyl. Again, it's activated by another amino acid, as we saw with the chymotrypsin. And this gives the tetrahedral complex. Water swims in after you lose choline. This is choline. Water comes in to reactivate the enzyme. Because at this point, the enzyme is dead. Again, all these enzymes, as we talked about last week, it's a two-step reaction. This enzyme is dead now. It has to be reactivated. Water does the job, attacks the carbonyl, break that bond, and you get back the enzyme. This happens 20 million times a second for 1 active site. Actually, 20 million times a minute, so a little bit slower than I said. So the function in this little cartoon, you'll learn more about this, I think, in medical school or biochemistry. The nerve impulse comes down, and at that point, the choline is converted to acetylcholine, and that completes the nerve impulse. As soon as one impulse goes over to the muscle end plate, then in fact the acetylcholine has to be removed, has to be hydrolyzed off, and that's the function of acetylcholinesterase. If you inhibit this enzyme, these guys stay there, the nerve keeps firing, and that's what leads to the problems I showed you guys. So what happens with the nerve agent now is Sarin goes into the active site, unfortunately, reacts with the serine amino acid. Again, it's probably O- here, and that gives a very strong PO bond. The phosphorus-oxygen bond is very strong to begin with. And if the nerve agent has a bulky group here, isopropyl, then the normal nucleophiles in your cell, maybe water, will not reactivate it. And now you've killed the enzyme. Lange and Kruger, the compounds they made, just had a methyl group here and an ethyl, and they noticed the effects, but they recovered because normal nucleophiles would get in and break this bond by attacking the phosphorus. The bulky groups stable to hydrolysis. The evidence for this is amazing. You can take an animal, expose him to nerve gas, hydrolyze him totally, 6-normal hydrochloric acid reflux for 24 hours, as we've talked about. You break all the peptide bonds in the acetylcholinesterase, which is a protein, and you can isolate the serine still attached to the nerve agent, or the enzyme still attached, showing you how difficult it is to break that bond once you've been exposed to the nerve agent. It's more toxic if you have a positive charge here, and that then led to the development of VX, which has a positive charge there, attracted to the negative charge, and that's why VX is so much more toxic than Sarin. And again, if you have small groups here, you can hydrolyze these very rapidly. Isopropyl groups, you never get it off with normal hydrolysis. And Somon, this very bulky group made by Kuhn in Heidelberg, very resistant to the antidotes. And the one antidote is amazing, as you'll see in a minute. Physostigmine, the drug of divine justice we talked about, reacts. Also, right here, the acetylcholinesterase attacks right here, and this whole thing is stuck onto the enzyme. Some other compounds the French have made, also very toxic. And parathion, the pesticide that is just a little bit less toxic than Sarin, no longer used, of course. And it killed a bunch of troops some time ago in Honduras. as you can read here. And in fact, it was a case not that long ago in India where a lot of kids died. They didn't have access to the antidote that would have saved their lives, I'm sure, at the time. And they ate food out of a metal can that was used to store organophosphate insecticide. Even though maybe just a little bit of the insecticide on the bottom, it turns out to be extremely toxic, low LD50. And this is that compound. Okay, now the antidote. Now this guy who died not that long ago, working, I think, in Colorado, came up with the idea, the way to detoxify, to get that phosphate unit off of the enzyme, you want to design a compound that has a pyridine ring connected to an aldehyde. But rather than the aldehyde, he made the oxime. So that was on the last exam, or the one before that. If you have an aldehyde, hydroxylamine makes oximes. Now this by itself is not good enough. But what he did, he methylated this. And that induces this proton to fall off. So in one step, he has the perfect antidote, the positive charge to be attracted to the negative charge in the active site. And the minus here is a great nucleophile, loves to go after phosphorus. So this antidote is beautiful. Attracted here, minus, plus, negative harpoons its way in and just takes off the phosphate, restores the enzyme. And this antidote, PAM, has really saved many, many lives who have been exposed to things like parathion, soldiers who have been exposed, chemical warfare workers down in Bethesda, exposed to this, to the nerve agents, were saved because of PAM. Now, actually, skip over that. Now, in addition to PAM, you need atropine, I mentioned earlier. The function of atropine is to sweep off the acetylcholines from the muscle end plate. So PAM restores the enzyme, but then you have to open up the channels again. You have to take off the acetylcholines, and that's the function of atropine. And you can see, here's an experiment with mice. You give them DFP, which is the lethal dose. As you can see, they all died because you didn't do anything. You give them just atropine, that's not good enough. They all die, even with a larger dose. But if you give them PAM alone, you can see 22% will survive this massive dose. This is now 4 times the lethal dose. But the combination of PAM and atropine, as you can see, a little bit of atropine and PAM, they all survive, even given a 4 times the lethal dose, as you can see. And this is what the soldiers carry today, I think, in Iraq and Syria in case of exposure to nerve agents. PAM is here, atropine is here. So it's injected simultaneously into your thigh if you experience any of the problems we've talked about with nerve agents. Okay, then finally, this again shows how VX is so much more toxic, at least in mice, than the other 3 we've talked about.